work is focused on developing tools and approaches that a grower can use to improve production efficiency and produce sweet potato of consistent yield and quality. First, we try to understand how sweet potato storage root formation works. Second, we work on optimizing irrigation and fertilization to optimize sweet potato yield and storage root formation. Now we're focusing on the quality of transplants to see how it impacts stand or survivability and yield quality and consistency. Now, managing irrigation and fertility is a bit easier because you can apply fertilizers and irrigation across the field uniformly. However, transplant quality can be highly variable, and it varies from field to field and from grower to grower. We borrowed a page from Manufacturing and Business in how to improve the delivery of products and services. In particular, we're testing a method called Six Sigma. This is essentially a set of tools designed to improve the delivery, remove inconsistencies and product defects in order to deliver a product of consistent quality. Six Sigma has several tools that enable a team to brainstorm and how to improve its product quality. One of its tools is called a fishbone diagram. Essentially, it shows the product output, how to improve the product, and it shows what features contribute to the quality of the product. We are trying to develop such a diagram for sweet potato to enable a grower and his team to brainstorm and identify areas where they can improve the quality of the transplant. So today we are going to demonstrate the application of Six Sigma on the production of quality transplants in terms of diameter, in terms of thickness, in terms of length. This row was planted with slips that were not sorted, meaning they were clear-cut from the plant beds, put in containers, and planted directly to the row. As you can see, this hill has inconsistent sizing, one slightly large root and two smaller roots. Going to the next hill, we only have two roots, again, of inconsistent size. We would like to see a more uniform sizing. Going over to the next hill, we see four storage roots, which at 77 days might grow to a bigger size at harvest. So we are looking for this. However, it's inconsistent. You go from one hill with only two roots with non-uniform sizing to another hill with four roots with more or less uniform sizing. The next hill over, we have two slightly large root and two smaller roots. So in this row, we applied our Six Sigma approach in ensuring that the slips that we cut from the plant beds have uniform thickness, length, and number of leaves. As you can see, this hill has three uniform size roots, maybe two smaller ones. This hill has four uniform size roots and maybe a slightly smaller one. This hill also has four uniform size roots and maybe a smaller one. And again, the next hill has four uniform size roots. In other words, at harvest, we are expecting to dig 4 US number 1 size roots per hill, compared to the other row where the stand was inconsistent, the number of roots were inconsistent. There's more potential for the grower to expect higher economic returns.
In addition to the slip quality treatments, we also established small nitrogen, phosphorus, and potassium reference strips, or simply NPK reference strips. We recommend that the producer conduct soil testing to determine the optimum nitrogen, phosphorus, and potassium requirements of a particular field. These NPK reference strips were designed as a tool to assist a producer in validating the effectiveness of these nutrient inputs. The NPK reference strips also provide guidance for in-season nutrient management. For example, the reference strips can provide leaf tissue samples to rapidly diagnose potential nitrogen, phosphorus, or potassium deficiency issues. In addition, the N reference strip can be used to calibrate optical sensors that are currently being tested to monitor in-season nitrogen status of crops. We harvested the demo plots at 91 days and measured the storage weights of the various experimental treatments. The results demonstrate the potential usefulness of NPK reference strips in validating fertilizer inputs, as well as to provide guidance for future plantings. In particular, adding the recommended nitrogen, phosphorus, and potassium amounts based on soil testing resulted in a 57% increase in total yield compared to not providing any fertilizer inputs at all. These findings help to validate the importance of these key fertilizer inputs that are used by producers. The NPK reference strips also demonstrate that adding nitrogen, phosphorus, and potassium beyond the recommended amounts do not result in increased yields. For example, doubling the nitrogen resulted in a 15% decrease in total yield. The NPK reference strips also show that the potential benefits of ensuring slip quality are only achieved with optimum fertilizer inputs. The results demonstrate the potential benefits of NPK reference strips on farm. The NPK reference strips are easy to set up and offers many potential benefits to sweet potato producers. We thank Larry Fontenot for allowing us to demonstrate NPK reference strips on his farm. We look forward to working with other producers in testing and evaluating NPK reference strips on their farms.
The findings demonstrate the potential benefits of NPK reference strips for on-farm nutrient management. It also demonstrates the importance of optimizing nutrient management in order for slip quality management to work. We thank Larry Fontenot for allowing us to demonstrate NPK reference strips on farm, and we look forward to working with other growers in testing and evaluating NPK reference strips on their fields.